In this video, I'm going to review pH. And pH, remember, is just a convenient way to express the concentration of H3O plus ions. That is to say, it's very useful when we're dealing with acids and bases because the H3O plus ion is a crucial entity when we're dealing with those kinds of reactions. Now remember, when we're dealing with pH, we are using the negative base 10 logarithm. And if you'll remember from math class, the base 10 logarithm is essentially a way of zooming in on the decimal places present in a number, okay? So say for instance, the base 10 logarithm of 1000, the base 10 logarithm is actually 3. Because notice, the decimal point can move over 3 spots in order to get to a simpler number, okay? Now let's do another one. So if you have a number like 100,000, okay, the base 10 logarithm for this number is 5. Because if, look, 1, 2, 3, 4, 5. Moving over 5 decimal points gets you to a base 10 logarithm of 5. Now let's go the other way. Now what if we have a base 10 logarithm of something that's less than 1, okay? Now let's do something like this, 0.001. Now what is the base 10 logarithm of that guy? Well, it turns out the base 10 logarithm is actually minus 3. So this minus here with the negative 3, this minus is the reason we do a negative base 10 logarithm when we're talking about the concentration of H3O plus, okay? Since when we're dealing with the concentrations of H3O plus, we are looking at usually maybe like 1 times 10 to the minus 1, all the way up to 1 times 10 to the minus 14, okay? And remember, this right here comes from the K sub W for the autoionization of water, all right? So we can have a minimum of the hydronium ion concentration as 1 times 10 to the minus 14. So if we're applying a negative base 10 logarithm to each of these values here, so for 1 times 10 to the minus 1, that gives you the negative log of 1 times 10 to the minus 1. Negative log here is actually just 1. And then for this guy, the negative log of 1 times 10 to the minus 14 is 14. So it's a very easy way for us to report the concentration of our hydronium ion by applying the logarithm. Now remember, we already talked about in class how when you have a neutral solution, you have a solution that has the equivalent concentrations of the hydroxide ion and the hydronium ion. And remember, we learned that each of those are 1.0 times 10 to the minus 7, and this is just based on the K sub W, right, which just says that the K sub W is 1.0 times 10 to the minus 14, right? And this is also equivalent to the H3O plus times OH minus. Okay, now if we take the pH of this particular concentration of the hydronium ion, the pH, which is just the negative log of 1.0 times 10 to the minus 7, the pH comes out to 7, okay? And remember, all of this is reported at 25 degrees C. Now what if we have a concentration that's not quite so clean as just 1.0 times 10 to the minus 7, right? Now what if we have something that, so we can use these significant figures here, we can use these to get to kind of where in between, where on that logarithm scale you're going to be. Okay, now let's look at 9.8, for instance, times 10 to the minus 7, right? So this is what you're looking at. Okay, now if you look at this number, it is very close to 0.000001, right? And this right here would be 1 times 10 to the negative 6th. Well, this guy right here, since it's really close, this actually, if you take the negative log of this number, the negative log of this number actually ends up being to 6.01. That is to say that it is almost all the way down to 6 decimal places removed, which is where the 6 comes from. It's getting really close to 6 decimal places removed from the 0 point part of the number. Now what if I go in the opposite direction? If I have 1.1 times 10 to the minus 6, which is just slightly higher, right, than 1 times 10 to the minus 6. If I have 1.1 times 10 to the minus 6, the negative log of this number will actually be 5.96. That is to say that it is very close to the 1.0 times 10 to the minus 6, right, but it's not quite. It's a little bit higher of a number, so the negative log is going to be a little bit lower of a number. If you have a concentration of H3O plus that's slightly higher, right, 1.1 times 10 to the minus 6 versus 1 times 10 to the minus 6, that means you have a slightly more acidic solution. Thus, you have a lower pH. So this actually brings me how we figure out the sig figs when it comes to pH. So if we have a number, say 3.5 times 10 to the minus 4, 3.5 times 10 to the minus 4. When we're dealing with the significant figures for pH, the number that is the exponent up here will actually give rise to the number to the left of the decimal point in the pH, right? So the logarithm of this minus 4 will actually give rise to a 3 to the left of the decimal point for our pH. Okay, now this number right here is where we go to determine how many significant figures will be included in the overall pH. That is to say that this number has 2 sig figs right here in this part of the number, and this will be included in 2 sig figs to the right of the pH on this side. Okay? And they're obviously not a linear relationship between, notice that I have 3.5 here, but when I calculate the negative log, it comes out to 0.46 on the other side to the right of the decimal point. Okay? But it's important to note that the number to the left of the decimal point tells you where on the scale of magnitude you're going to be, right? How many orders of magnitude will be included with this particular concentration, and the number to the right of the decimal point will be the more specific concentration of the hydronium ion. So really the take home with all of this is that I want you to be able to distinguish that when you're dealing with pH, the pH change is dealing with orders of magnitude. So say if you have a pH of 4 versus a pH of 6. So instead of saying, well, the concentration will increase twofold by going from 4 to 6, the concentration of the hydronium ion will actually be 100 times greater, right? So 2 orders of magnitude greater when you go from a pH of 6 to a pH of 4.